Hello everyone. First of all, today or tomorrow, depending on time zone, SpaceX is going to first relaunch a reused landed rocket, which is pretty much history in the making. I will obviously watch this live, and I will probably mirror this live on my channel. I've kind of figured out live streaming on YouTube. It's a bit tricky. You need to install a special software. I haven't bought it yet. I have a trial version, and it's kind of technically difficult, but it's kind of working too. I did a little test. I'm probably going to make a few comments on it, maybe answer some questions or something. I'm not entirely sure yet. Anyway, to get to the actual topic, today I'm going to talk about something that both KSP and Orbiter and actually most other simulators or simulation games don't really teach you much about. Surprisingly, actually. And that is space navigation, deep space navigation, and also a little closer to Earth space navigation, which is a lot more complicated than just than any other mode of transportation, and that's really one of the most challenging aspects. I mean, programming a rocket to land on a drone ship is easy if you know everything. If you are perfectly all-knowing and you have precise information over the exact state of the rocket, then that's easy. The trick is you first have to know where you actually are and how you're actually moving with enough precision to actually predict the path, and it doesn't get easier when you try to get to a faraway destination or when you try to position a satellite precise enough to work as a navigational satellite for vehicles on Earth. Now, there's several ways you can navigate in space. There are a few exceptions. I'm going to talk about those later, but mostly there's like 2.5 categories. There's two main categories and one smaller category and a few extras. Now, first is optical navigation. Now, that again goes into several categories. The first is a star tracking camera, which almost every spacecraft or satellite nowadays has. That's basically a high resolution camera that just films the sky around it and finds known constellations, and since stars are very far away, even if you move halfway through the solar system, they seem to hardly move at all. So you can see how your spacecraft is exactly oriented if you just look at the constellations. And if you do something similar to celestial bodies within our solar system, you can then also kind of find out your position, because if you know your orientation and you know the moon seems to be over there and the earth seems to be over there, then you have a good idea of where you might be. That's just directional optical navigation. Then when you get really close to a celestial body, or theoretically it might also work farther away, but that's impractical, you can also analyze the actual image of what you're looking at. For example, if you look at the Earth and you're a bit away from Earth, but you look at the Earth and you see there's Europe right in the middle, then you can tell that given the current time, you have to be into this direction from Earth, and so you have to be somewhere there. This is actually not that useful if you already have a star tracking system, because then you already know the direction towards Earth if you see Earth. But that's something that is usually done when you're orbiting really close. You can also tell the distance to a planet or moon if you look at it and it's relatively close, so it's still enough pixels in size that you actually get some precision. You can see how big it appears, and then due to perspective, of course, the bigger it appears, the closer you have to be. But actually, if you have several celestial bodies and a rather precise camera, you already have kind of an idea where you are. Then there's radio navigation, which mostly uses radio stations on Earth, of course. They can send a signal to the spacecraft, and you can send it back, or you can compare it to a precise clock, and then you know how long it traveled and the speed of light, so you know the distance. You can also do this with several spacecraft and several receivers, and so you can navigate precisely around more distant celestial bodies. You can also use natural occurring radio sources like pulsars that send out a frequent radio signal in a precise and a precisely timed pulse. So you then have an exact timer, and you can compare that to a timer that you get from Earth, for example. Of course, you can also use radio signals to find out direction. You can use a directed antenna. I mean, in deep space travel, you're usually radioing over such long distances that you're going to use a precisely aimed directed antenna anyways to get any reception at all. And by seeing how you have to point that antenna to get a signal, you can then find out in which direction the sender is, and so you can do this in both ways, and then you know in which direction the radio station has to be, or in which direction the spacecraft has to be. Then in the more old-fashioned, it's still sometimes used, but it's less precise, but it's a really versatile but really unprecise way to navigate is inertial navigation, or just internal integration. There are no sensors that just perfectly tell you where you are and how fast you're moving, but there are just sensors that can sense acceleration or angular velocity. And so if you know how you started at the launch pad at 0 velocity compared to the ground, you can then add up the values of an accelerometer and an angular velocity sensor, or you can just use a gyroscope and hope that it works without friction or with relatively little friction to tell your orientation compared to the orientation on the launch pad. If you add those up, you can kind of calculate your path since your launch, and thus your current position and speed, but it's kind of imprecise. It has to work perfectly all the way. Of course, you can kind of settle it down or make fewer measurements in an easily predictable section of the way, like a really long Kepler orbital piece. But then, of course, hoping that everything just goes exactly as predicted is also a way of navigation, but it's not precise at all. And all the errors in inertial navigation add up. So especially over a long time, it gets kind of unprecise. But if you use the right algorithms, it's actually possible to land a lander on the moon using mostly inertial navigation. That's how the first unmanned probes landed on the moon. Of course, back in the Apollo era, that time, there wasn't much in the way of really high-definition digital imaging or image recognition. The Apollo spacecraft actually had a manual star tracker. The astronaut actually had to use a visor and an instrument, and the computer would ask the astronaut to point an instrument at certain stars and then measure how the astronaut moved the instrument and thus track the stars instead of analyzing an image of a camera. Among radio navigation, you also have the use of Doppler measurements. You can measure the velocity of a spacecraft relative to a station along the distance axis. I mean, you could do that by just measuring the distance using the time the signal needs and the speed of light several times and subtracting it. But you can also use the Doppler effect, the shift in frequency as the spacecraft moves. And you can use very specific properties of celestial bodies. You can use, as long as you're close to Earth, for example, you have the Earth's magnetic field that you can analyze to kind of tell your position and velocity relative to Earth. You can't tell all of it, but you can, if you know some of it, you can tell the rest. For example, a compass kind of works in low Earth orbit, but it's not that much use on its own. You can use really distinct landmarks. Rosetta, for example, mostly navigated around its comet using a high-definition camera, and analyzing the shape of the comet, which of course is relatively easy if the celestial body you're orbiting around is more rubber duck shaped than spherical. And it also had no weather that would influence the images that you take of it. And that's about the most used ways to navigate in deep space, because there's a few hypothetical special ways that are hardly ever used. And for example, as long as you're close to an atmosphere, you could analyze similar to an airplane pitot tube or an airplane altimeter, just that you wouldn't classically measure the pressure because there's not enough pressure around, but you could kind of count the particles around you and measure how they hit you to measure your altitude and your velocity relative to an atmosphere, as long as you're in the uppermost layers of an atmosphere, even if it's hardly anything there. Like in low Earth orbit, you could still theoretically use the last little bits of atmosphere to measure your altitude and velocity. But that's never actually used. That's just a hypothetical concept. Anyway, I hope that was kind of interesting, and thanks for watching.